Institute and has been here doing graphics and computational photography at University of Science for the past, what, 16 years now.
Yep.
And we're delighted to have him back and hear what he's been up to in the last 2.5 years since he's been home.
Thank you, Tamara. It's a pleasure to be back. This room certainly has changed a lot since the last time I was in this building. But okay, so today I want to tell you a bit about computational imaging and photography. But I'm going to start off a little bit to tell you a little bit about KAUST, because I know that I've just dropped off the radar, I guess, for most of you, and you might have been wondering what I've been up to and what it is that I signed up for these 5 years. I'm the director of the Visual Computing Center at KAUST, where KAUST is a very young university. 5-year celebration was about 1.5 years ago, which means that I've actually been there for 1/3 of its history now, which is a little bit scary. But it is a very ambitious university project, graduate-only university, located in Saudi Arabia, right on the shores of the Red Sea. So this is Jeddah. We're just maybe an hour north of Jeddah. By the way, my office is there. This image is so that you understand it's not all desert, right? It's 1/2 space is desert, the other 1/2 space is actually water. So it's an enclosed campus with a Western-style university. Here are some statistics, outdated by maybe 9 months or so. So the numbers have changed a little bit. We're at over 900 students now. This is, again, graduate-only students. I think we're over 7,000 on the number of people living on campus. Extremely international. I mean, even by UBC standards, I would say, very, very international community, really people from all over the place. What you'll notice is that we actually have more school children than we have students, which shows you that we have a lot of young families actually on campus, including lots of young families from the West. We have a very high percentage of postdocs and research scientists compared to the graduate students, as you can see. This is one of the ways in which we're able to really do a lot of really world-class research. We're at about, I would say, 2/3 capacity right now for faculty members. I mean, we're at about 145, I think is the latest number I heard. We're going to go up to about 230 or so. That's going to be the end of our growth. And the model is kind of like small but very good, so sort of like a Caltech kind of model. That's the idea. The other thing I don't have slides for is actually you might be surprised to hear about the gender balance. So we have about 1/3 of female graduate students across all campus and also in computer science. So graduate school, computer science, 1/3 of the students. Okay, so enough about that. I mean, basically, if you want to know a bit more about KAUST, I can maybe answer some questions later. Just very, very briefly about the center that I'm at. We have 5 faculty right now. We're just hired a new person who's going to join us in August. And that's basically the space that we're in is starting with imaging devices, computational imaging, computational display. That's what I'm going to be talking about today. Then component on image understanding, so basically classical computer vision, problems, tracking, understanding, segmentation, those kinds of things. By the way, we have a startup company already in the center, which is actually the first Saudi company that's completely foreign owned. We have a computer graphics group focusing on geometric modeling. That's an area where we just hired. So physical simulation, and then large-scale visualization to tie everything together. And I'm not going to spend any more time on this, but this is basically a nice group. We want to maybe go up to like 7 or 8 faculty or so in the next 1 or 2 years. Okay, so I want to talk about my own research today, which is basically in this early stage of this pipeline. basic computational imaging devices and computational displays. And so let's look at the history of photography. So the most simplest camera that you can build is the pinhole camera. So you have a room, you have a hole in the wall somewhere, and it projects an upside-down image of the outside scene onto the wall. And this is, really very, very old, about 470 to between 470 and 390 BC. Nuxi in China. That's the first preserved record, but the suggestion is that it's been much, much older than that. About 1,000 years ago, Ibn al-Haytham had a full geometrical analysis of this camera obscura, or the pinhole camera. So he was actually Iraqi, so he was born in Basra. And I don't know how many of you saw that last year was the UNESCO Year of Light, which basically celebrated 1,000 years of optics. And that goes, the 1,000 years of optics comes from this guy. He wrote a 7-volume book on optics, 1,000 years ago. So this is sort of transient, right? So you project an image upside down on a wall, and then now the next step is how do you actually preserve it so that you can actually look at the same image later. And so chemical photography, sort of in the 1820s, where the first steps were made. And then 1969 was the development of charge-coupled devices, which is one of the first technologies for electronics image sensors. And what I'll try to convince you of in this talk is that we're sort of in the middle of another very major shift in how cameras are being built, and that's sort of the advent of computational cameras. Okay, so where computation is actually a fundamental part of the design process and the operation. Okay, so computational imaging and display. This is how I see it all fitting together. So it's an interdisciplinary area between computer graphics, computer vision, optics, perception, imaging, inverse problems. It's all in there. And if you look at computational imaging, the basic task is that we want to co-design the optics, the electronics, and the reconstruction algorithms to give us the best performance for the cameras that we want to design, maybe application-specific cameras. Okay, so in the past, what's been done is that the optics community created the best optics to create the sharpest image onto a 2D image plane, and then the electronics community did the best, tried to do the best job to sample that information, and then the computation side, to the degree that it was present at all, was just doing a little bit of cleanup in the end, right? And I think what we're seeing now is more this notion that we actually have optics that does a general encoding of information about the scene onto a 2D image sensor. And that encoding might not be directly useful for human consumption at all. It's just a 2D array of numbers. And then this 2D array of numbers is being sampled by electronics and then decoded by the computational part. So you have encoding, decoding. And of course, when you look at it that way, it's clear that you want to design the different components together. And that's really what computational imaging is about. Computational display is a dual of that. So basically now we have computational encoding of image information, and then basically a decoding by the electronics and the optics of the display hardware. So I'll talk about that a little bit as well. So today, what I want to talk, I basically want to illustrate this principle by just talking about a bunch of projects that seem at first sight completely unrelated. And then I will tell you what the underlying joint methodology is at the end. It's a very, very flexible framework to think about imaging. And so really all these different topics, they seem like they're really individual projects that have nothing in common. So I'm going to start with Schlieren image or fluid imaging. And so the idea is that we want to image hot gas flows. Okay, so this is a scientific application or engineering application. Let's say we want to image how hot gases flow in space. And I chose this particularly because in computer graphics we're often very focused on sort of entertainment applications. And I just want to make the point right in the beginning that everything I'm talking about also has applications in the sciences and in engineering. So this is a fluid imaging application. So the idea is we have this burner. It has a hot gas flow on top of it. And we want to reconstruct the 2D flow, 2D imaging of the flow, but also we want to reconstruct a 3D volumetric representation of this flow. Okay? And so the way we're going to do this is by basically tracking, by basically observing this hot air flow against a high frequency patterned background such as this one. And then we're going to track the minute distortions that this creates in the image plane. And that gives us 2D distortions, which the computer vision people among you will know as optical flow. Okay? And from this, we can actually reconstruct the 3D field of refractive index gradients. And from that, we can reconstruct the refractive index field on a volumetric setting. So here's this in a little bit more detail. So here on the right-hand side, we have our camera. So we have a camera lens and an image plane. We have our high-frequency patterned background here. And basically, if this is an empty volume, right, and just ambient air, then what happens is, of course, all these rays travel straight, and A gets mapped to A, B gets mapped to B. But if we introduce hot air here, then basically the change in the refractive index here will create sort of a Fata Morgana kind of effect where the ray gets actually deflected, and all of a sudden this point B gets actually imaged on the image plane where previously we would have A located, right? And this displacement in the image plane we can track very easily computationally, because this is just what computer vision people do when they say optical flow, right? It's just a 2D displacement tracking of these individual points. So when we do that, we observe something like this. So I'm going to play this. This is, I swear it's a video, okay? But it's not just a still frame, but you might be hard pressed to see any motion. Okay, this just shows you. Yeah, so that was the video. Okay, I'll play it again. Focus on this top left area here, and you might be able to see just a little bit of motion just now. Yeah. Okay, so this is a video, but of course, if you see this, it's not really something that we as humans can interpret, right? And that's basically what I meant by optical encoding. This is an optical encoding of information about the real world, but we can't interpret it directly. So let's just do optical flow on this exact same data and trace the 2D displacements in the image plane, and then code the displacement vectors, color code the displacement vectors. So here the hue is the direction, and the intensity is the magnitude of the displacement. And I'm just going to play that. And we get a little bit of a sense, I guess, of what's going on. That there's some turbulence or whatever. But at this point, we can actually go back to the physics. And the physics tells us that this gradient, this displacement that we measured here, is actually the gradient of the phase of the light. So if you assume that there's an incoming plane wave of light, then this gradient that we've just measured is the gradient of the distorted phase of the light as it propagates through this medium. And as such, it's an integrable function. So if we just take this vector field and actually integrate it with a Poisson solve, we should be getting a phase measurement of the light. And in fact, that's exactly what happens. So now I would argue that we get a very good idea of what's actually going on in this data set, right? So this is a 2D visualization of the flow that is generated by this candle. And I promised you 3D, so for 3D it gets a little bit more complicated. So you actually have to have a camera array. In this case, 16 cameras. The room was over in the Asus building, 7th floor. We have our patterned, so 16 cameras, patterned background, little reconstruction volume here. And so then we do these 2D measurements that I just showed you, and we're going to do tomography on this, and I'll explain to you why it's tomography. So basically, if we have this problem of the distortion, basically the propagation of light through this medium can be described by the Ray equation of geometric optics. And so there it is. And we can split that into a bunch of ODEs, and then basically one of them is more interesting than the other, and that's the one down here, where basically, so what this equation down here says is that the change in direction that our light path takes is directly proportional to the gradient, or the local gradient of the refractive index field, right? And so when we take this equation, we can actually set it up as an equation like so, where basically we have the outgoing direction here, the incoming direction, well, we're working with cameras, so we're going the other way around, okay? So we'll call the camera array the incoming direction, the outgoing direction is the one near the background. And so this outgoing direction is the incoming direction, plus the integral over all the different changes in direction along this light path, and they're related to the local gradient of the refractive index field at each point, right? So basically, if we look at this from with just sort of an Euler integration kind of interpretation, we just step along the path, and we always compute the local, or find the local gradient of the refractive index field and add it to our direction, and then we'll basically get the change of the rays in the end, right? So basically, when we set it up this way, we have basically this equation down here, where on the left side we have these two directions, which is camera calibration, and then this one is this imaging method that I just told, this 2D imaging method that I just showed you before, the optical flow. So this left-hand side here is actually known, and the right-hand side, what we want to know is the gradient of the refractive index field, and that's related through the integral over the path. So this is actually a standard tomography problem in the end. And so now we can set it up as a standard tomography problem and solve it. It just ends up being a linear equation system that we need to solve, and voila, we get 3D flow. In this case, it's a turbulent flow that is, comes from a burner, from a gas burner. We can also do that, so that shows that we have quite a bit of detail in there. This is 3 candles that are burning. It's much more laminar flow. It shows you that the noise is pretty much under control for this kind of imaging, even with just 16 cameras, which is a very small number of cameras to use in tomography problems. And then here, because of the particular way the image formation is done, actually this refractive index field that we've just recovered is actually directly related to the temperature. So we can actually do a temperature, it's basically a thermometer also. You can just overlay the temperature of the gases back onto the original input videos, and then see which of those candles is hotter. So this one, for example, isn't burnt hot. So we've done a whole bunch of other work on fluid capture that I could get into, but I think I want to really just give you an overview of all the different kinds of things that you can do with computational imaging. And so I'm going to move on to a completely different topic, which is computational imaging with inexpensive lenses. Okay, so this is a fairly recent project. And it starts out by this observation. So you have a cell phone here. This is the press photo that came out when the iPhone 6 was first released. And it looks like the press release image looked like this. And then the iPhone 6 was shipped, and it was not quite accurate. There's sort of this camera sticking out here, right? And like this, right? And so basically, so they photoshopped it away. And so basically, the reason why this camera is sticking out is, or most cameras now, most cell phones now have a slightly bigger portion, right, where the camera is, right? And the reason is because when you get to flatter and flatter cell phones, what's limiting the thickness of the cell phone now is actually just the thickness of the optical stack of your camera. Okay, so all the lenses and the spacing between the lenses and the sensor, that's limiting how thin you can make a cell phone now, right? And so that's basically one of the problems that we want to overcome. Here's, by the way, a very recent camera from Asus, or cell phone from Asus, that actually uses this kind of setup. So this is the lens pointing forward, and then they redirect it horizontally, and the image sensor is like this. So this would be mounted, basically a camera that's mounted sideways. And this is actually the first zoom lens on a cell phone. But again, it just occupies a huge amount of space. And so can we do better than that? Is one of the motivating factors. So when you get right down to it, this is an actual diagram of a camera objective for single lens reflex cameras, SLR cameras. And you see all these different lens elements. And so you might ask, why are they actually needed? Why do we need to have so complicated lenses? And the reality is that they're needed because our image sensors are having higher and higher resolutions, which means that our optics needs to focus better and better and better. And so with real lenses, we have aberrations, so imperfections in the focusing, the geometric, spherical, chromatic, all these kinds of things. And in order to correct for those, we need more and more lens surfaces, more and more degrees of freedom to basically do the correction, right? And so that's why our lenses get heavier and bigger and every year. So that's what we want to overcome. And so in this project, we basically said, can we go back to, can we wind back the clock 100 years and just image with the simplest lens element that you could possibly imagine, which is a single plano convex lens, right? So you have a lens that's flat on one side and it's a spherical surface on the other side. And it will have horrible distortions, but maybe we can actually correct for those with computation. And so this is what the horrible distortions look like. So they're called point spread functions. So they are, you see there's a lot of chromatic aberration in there, so different behaviors to different wavelengths. And it's very large, so these blurs are about, I think, 70 pixels on these squares, 70 pixels on the edge on a 14 megapixel sensor, I think it was at the time. And so you may have heard, if you're working on numerical methods, people have been working on deconvolution or deep blurring for a long time, but not with these kinds of point spread functions, right? When you look at this and your inverse problems becomes really horribly conditioned if you try to deconvolve with this, right? So you need to have some extra source, special source, if you want to actually solve these kinds of problems. And so the idea is, okay, can we really do this? And so here's what happens because of this poor conditioning when you just apply old school deblurring methods on this, right? So you have your blurry image, which is blurry and has chromatic artifacts from this point spread function. And then if you just apply a deconvolution, you get these kind of colorful ringing artifacts here, which are really very disturbing to the image quality. Okay, this is because just numerical conditioning. Yeah.
So could I ask you to explain again what the picture was on the previous slide?
Oh, sorry. Okay, so all right. So this is basically different blur kernels for different image regions. Okay, so this is the so because it's actually not really a convolution because you have different blurs at different in the center of the image versus the corners of the image, and so you see a symmetry here, right? So this blur kernel is kind of similar to a mirrored version of this one like this one, right? So basically, in the center you get more like disks. And then you get what's called coma, which is these weird cross-like, comet-like features on the periphery. Does that make sense now? Yeah, it's basically the blur kernel, but for different blurs for different image regions in a realistic kind of setting. So you can locally treat it as a convolution, but not globally. Yeah.
Are you trying to just invert the blurring operator? Because you can
Yes.
just replace it, make like a least squares thing with a constraint or something to study.
Right, so we're going to get to priors, and I'm going to get to that now.
Okay.
Yeah, exactly. So basically, you're basically the conditioning of this is horrible. So you cannot, I mean, if you just look at data terms or whatever, then you cannot actually do it. But you can design special priors to actually help you with the process, and that's exactly what I'm about to get into.
Okay.
Exactly. So, okay, so this is not really acceptable image quality. So let's move beyond that. And so what we did there is basically we discovered that, or we realized that, you know, the different color channels, of course, don't have completely correlated information in them. However, some information is very much correlated. For example, where the edges and images are, right? So if I have an edge in a green channel, I'm very likely to have an edge in a red channel. It might not be the same edge strength, and it might, you know, one might be increasing, and the other one might be decreasing, but they're going to be in the same place, right? And so this is what we can do what we can use to really better condition this reconstruction problem. So the fundamental problem for here is that deconvolution basically, or convolution with a blur kernel basically destroys certain frequencies. And then basically these frequencies you just don't have enough, basically you have eigenvalues that are 0, right? But if you have different blurs and different color channels, then different eigenvalues will be 0 for in the different color channels. And you can actually transfer information across different color channels to actually restore that information. So this is what we did, a cross-channel prior, basically, which says that the high gradients should in the images should all occur in the same image region, and you can basically write that up as a sparsity prior in the gradient space, which I won't be getting into at this point. But here, this is basically the idea, right? So you have a scan line, different color channels are blurred in different ways, which means that you know that you can also interpret it as a hue prior, so that the hue changes should be sparse in the image. That's another way of formulating it. And because you have different blurs and different color channels, the hue will be varying continuously over these red regions. But if once you have the sharpened image, then it should be limited to the edges of objects, right? So this is this cross-channel prior that we developed, and it's very effective. So here's a video of this is a pan over an image plane. Okay, so this is a 14 megapixel sensor, and we're going to pan over the image plane. On the left you see the sensed image, and on the right you're going to see the reconstructed image. And we're getting very, very close to you know, a good SLR image. I don't know if there's a way to control the lighting, maybe, but yeah, maybe on the TVs it might be better than on the projection screen. Maybe that's better. Yeah. Okay, so there are some artifacts left, but I mean we've basically pushed it to the limit of you know, there's some text that becomes legible, etc.
Thank you.
So so the what we were able to show here, that this is quite promising. Of course, you don't want to be as aggressive as I just showed you. You probably don't want to have camera optics that just have a single lens element. But maybe rather than having a dozen, you can have 2 or 3, and you give yourself a budget, and you actually design this optical system to produce the point spread functions that are easy to invert, so that the inverse problem is actually better defined. And then you can have simple objects combined with computation to actually give you sharp images. So there's a startup company called Algolux in Montreal that has licensed this technology and is actually working on exactly pushing that into the mobile market. So what we've been doing lately is, and this will be at SIGGRAPH later this year, is actually analyze whether we can use diffractive optics for similar kinds of things, because diffractive optics actually has a lot of degrees of freedom for optimization. And we can have very flexible design space with something that's basically just a sub-millimeter thickness, right? So you basically etch into glass a diffraction grating, and that's your lens system. And then the idea is to basically optimize that. Now the big problem with diffraction gratings is that they're highly, highly wavelength dependent. And so much so that the algorithm that I just described to you earlier will not work for these super extreme chromatic aberrations. But what the upcoming SIGGRAPH paper shows is that you can actually design diffractive optics in such a way that the point spread function is actually the same across all wavelengths over some design space. And that means that the central wavelengths aren't as sharp as they might otherwise be, but the blur is the same across all wavelengths. And so then you have a moderate blur which you can invert with the methods that I just described, or similar methods. And so at KAUST we actually have a nanofabrication facility where we actually can build these kind of diffractive lenses. And so here are some UBC students. This is Felix, this is Lei, who's sitting back there. And they were actually at KAUST getting trained in this in the use of this lithography facility in the nanofabrication core lab at KAUST. And they did the early work on building diffraction gratings, although the ones that I showed you earlier were actually built by other people later on. Okay, so I want to move along and talk about yet another project, which is Transient Imaging. Okay, so this is now basically imaging of ultra-fast effects. Okay, so what's a transient image? A transient image is what you get if you no longer assume that the speed of light is infinite. Okay, you will want to image effects that are related, that are happening at the scale of the propagation of speed of light. Okay. And so there's some pioneering work in the 80s based on that, so on this idea, so it's called light in flight. So Abramson had this idea, holographic method. So you assume there's a point light source somewhere over here to the right. And it's a really, really short pulse of light, right? It becomes a spherical wavefront. And the spherical wavefront propagates at different times. In this case, it interacts with a lens, and then what happens is the curvature of the wavefront gets reverted, and everything gets focused down into a point. Right? So this was the first image that they created with this method. This was a holographic recording method. Super cool work, but I mean, you cannot do large scale, or you cannot do even 3D kind of scenes. And then there was nothing for like 20 years, or 30 years actually. And then in 2013, so the early 2010s, there was a bulk of activity, so including work out of MIT, on using sort of femtosecond lasers and streak cameras to do similar kind of captures on 3D scenes. The problem with this kind of approach is really cool work, but the problem with this kind of approach is that you have hundreds of thousands of dollars of equipment, and then femtosecond lasers aren't really bright enough that you could put them in a room like this and really overpower all the ambient illumination. So we set out to basically solve both the cost issue and the issue of working in ambient light. And so this was our first prototype based on standard time-of-flight sensors. So basically you see a lot of hot glue on this prototype. And then control electronics, and then basically we get something like this out where the hue basically tells you time of arrival of the brightest light peak over time. A few months later we had this, so this looks surprisingly like a normal USB camera, which is what it is. You plug it into USB port, you have basically a special flash as a light source, and then this system was maybe like $800 or $900 material costs, and it can do similar kinds of imaging things as this light and flight imaging at room scales in ambient illumination. Okay, so let me tell you a little bit about how this kind of stuff works. Don't want to get too technical, but so I know a lot of you are not really in this area, but I want to give you a little bit of a sense of what the problems are that we have to deal with. So basically, the sensor that we have here is called a photonic mixer device, or correlation camera, or AMCW image sensor, or there are many different kind of terms for it. But basically at its heart, it's a normal camera that has a special kind of sensor. And this special kind of sensor has when you take an image, it has a finite exposure time of a couple of milliseconds. But within these couple of milliseconds, it can actually modulate the integration of time. So it can, one mental model that will do for this purpose is basically you can switch on and off the integration at very high rates. So let's say 100 megahertz, okay? So 100 megahertz, you can, so you do a third of a second integration or a hundredth of a second integration, but you can switch on and off the integration process at something like 100 megahertz. And then normally what you do is you would have a light source that's modulated with exactly the same base frequency, so something like 100 megahertz, say. And what happens is that so you have this modulated light going into the scene and then coming back to the sensor, and there's a phase delay in the time based on how long the light has traveled, okay? And then when you integrate, you're basically multiplying this incident light signal with this reference signal of the same frequency, and then you integrate over a long period of time. So what you've just done is basically you've measured the correlation of this signal and this signal, right? It's a cross-correlation sensor, right? It measures the cross-correlation of these two signals. And then if you want to use this as a depth camera, you basically have two unknowns that you want to solve for. One is this distance here, which is related to the depth of this object, and what is actually the reflectivity of this object here, right? So just how bright that is. And so this is the coefficient here, and this is the time offset. So you actually take two measurements, and then you can solve for both of those components. So this is how you use it as a depth camera. But the really cool thing about these cameras is that they actually encode a lot more information about the real world. And in the real world, we don't just have one light ray going through a single bounce from the scene back to the camera. We have what's called indirect lighting, right? Global illumination. And so here what happens is now in this simple example, we have two light paths that are additively overlaying on this sensor. And basically we measure the sum of these signals, and in practice it could be the sum of many light paths, or even a continuum of light paths. And what we want to do when we want to do transient imaging is basically we want to know for every possible travel time tau here what the corresponding amount of light is that arrives after this amount of travel time. And well, it's all additive, so this is actually a linear system. Okay, so I'm not going to tell you exactly how to come up with this linear system, but it's really just a linear system in the end. So we can actually set up a linear system. We do have to do many different measurements with different modulation frequencies, and different phase offsets here. So lots of details about this. But if you take many measurements, you can solve an inverse system to get a transient image like this. So these are water bottles. I'm going to play this multiple times. So you see things like surface reflection, scattering. There's going to be the light from this thing here will now light up the back wall here. And so this is an actual video of a light wave propagating into a room. Okay? So I'll play this again with some labels. I want you to look in particular also at this region back here. Where there's going to be a shadow coming up. So here's, okay, first surface reflection, then volume scattering. So now we're going to start seeing a shadow back here. And then the shadow fills in with a caustic. Okay, so the caustic is the light focused through this water bottle. And it arrives a little bit later than the shadow, because what's causing the shadow is the direct light that travels through the air. But what causes the caustic is the light that has to travel through water, where it travels slower, right? So this turns out is now actually the same kind of phase information that you would have, for example, in seismic imaging. So if you, in seismic imaging, you do, you set off some explosions and you have some microphones and you reconstruct what kind of material is down in the ground. And you have this kind of phase information. So here we have it optically now. And that means that if you do the right kinds of measurements, we can actually image or reconstruct the shape of these transparent objects. Now, other people have done this now based on this kind of setup. We didn't do that. We did something similar. We actually mathematically quite similar, which is imaging around corners, so imaging without direct line of sight. So here is the idea. So you have, let's say I have a camera pointing at this screen here, right? I pointed my camera at the screen, and I want to reconstruct you guys, okay? Without seeing you directly, right? So no direct line of sight. And so it's actually possible to do this. So basically we have, basically what happens is that the camera images this patch of screen. There's a laser pointer that basically emits the same thing as a short pulse of light from this, basically can be modeled as a point light source. This spherical shells of light kind of interact with the scene, scatter back, and then get reflected off of this patch. And with the time resolution that we have, we can actually see how distorted the wavefronts are that come back at this patch. And we image them, and then we can actually, from that, infer what the scene was, at least at some relatively low resolution, of course. It's not going to be like a laser scanner. But here's our scene. So 2 letters, same albedo at different depths. This is recovered albedo map, so the reflectivity map. And then this is the depth map. Here's a different scene with a single object depth, but variation in the reflectivity. And again, reflectivity map and depth map. And so we can actually reconstruct this kind of information indirectly. So, think about sort of imaging, in cavities. So say after an earthquake or something like that, you have no direct access to the cavity, but you can possibly look around a corner and see what's there, or if somebody's trapped there. Here's another application of this basic principle of time flight. Yeah.
On that one, do you need multiple cameras to get it to?
No, it's just one
time from one light. Because I just got the time from one light source.
Yeah.
Image.
Yeah, but I mean,
how do I get a 2D image out of that?
We have enough time resolution to actually see how the wavefronts are curved on this patch of wall. So basically,
I see. You can see
right.
different points on the screen.
So basically, different points on the screen will see the light coming back at different times, and from that time information, that high-speed time information, is enough to actually solve this inverse problem with some fairly complex regularizations. Okay, so here's another example where basically imaging through scattering media. So all of this is based on this transient imaging idea that I presented before. So the idea is that actually you can, this is just a transient image of a fish tank with a lot of, with some milk poured into it, right? So you can't see anything with a regular camera, but with a transient image, you actually see that there is actually a plane and other objects in there, right? So we find we can actually roughly triple the visibility in scattering media. And then more recently, also upcoming CDPR this year, we also used the transient image analysis to actually classify different materials based on the subsurface scattering properties, right? So if you have light bouncing directly off the surface, then it will just be a short peak of light coming back. But if it's scattering, then it will sort of be smeared out with some exponential decay. And you can use that to classify different materials. So in this case, we can distinguish between, say, a block of wax and an image of a block of wax printed out on a paper, right? And it will come back and say, this is paper, not wax, right? So you can think of applications in biometrics, for example, right? I cannot just print out a face. I have, it will classify as paper rather than skin. And then finally, based on the same kind of analysis, we can actually use Doppler Shift as well. And so with Doppler Shift,
Doppler time of flight has a new computational imaging technique that facilitates direct measurement of per pixel velocity.
okay.
Our technique requires a
spatial
time of flight
control.
camera and a high-speed light source.
Yeah. Okay, so basically, same kind of camera, but we're actually taking the Doppler shift of moving objects into our image formation problem as well. And that basically turns every pixel in our camera into a little LiDAR gun, okay? And so, let me see where we have the bike. Here we go.
As seen in this example, the output of our algorithm is a full field image of the
So
axial
basically
velocity.
you see
That
the
is the speed of the scene towards or away from the
velocity
camera.
map here of the biker. And
For
so,
precise control over the illumination and modulation frequency.
and there's another follow-up paper that's coming out also at SIGGRAPH this year. So I'll just leave it at that.
We introduced Doppler time.
Okay. All right. So I want to talk very briefly about displays. I know this is maybe some work that you've seen already. I just want to make the point that the display side is really the dual of the camera side that I've talked about so far. And really it's about now optical decoding of something that's been computationally encoded, right? And so we had a project here a couple of years ago, actually 10 years ago now, over 10 years ago now, we had this company, had this research activity with Lauren Whitehead's group in physics on building very high contrast displays, and so high dynamic range displays as they're called. And so the idea is that basically we want to have displays that actually really capture the brightness range that we encounter in the world all the time, right? And so basically the idea was very simple. So you take an LCD panel, which is a programmable transparency essentially, and you put it over a low frequency, a low spatial resolution backlight, in this case just implemented as LEDs that are optically blurred, and you put the two on top of each other, and then basically what happens, this magic that happens is that the contrast of this low resolution backlight multiplies with the contrast of the LCD panel, and you get a very, very high contrast image. So this was originally done with video projection as a backlight rather than the LEDs. So this was the very first prototype. There's a little museum upstairs on the 6th floor where you can see that in a showcase. This is a later version that Gerwin has been working with. Gerwin has been working on. That's I think somewhere on the ground level of Asus still in a side room. But you can see that the form factor of these displays is not something that you would want to have in your living room, but they're good experimental devices for doing perceptual studies. The more commercially interesting avenue is that you actually have, let's say, 2,000 LEDs for a 2 megapixel display, so roughly a factor ratio of 1,000 to 1 between the LEDs and the LCD pixels. And now you're actually faced with an optimization problem. So you have a target image that you want to reproduce, and you need to control the degrees of freedom in these LEDs, which is 2,000, as well as the degrees of freedom that you have in the LCD panel, which is 2 million, to give you the best image quality when you overlay the two. So you can basically write this up as some kind of an optimization problem that looks something like this. The metric is somewhat undefined because ideally you would like this to be some kind of perceptual metric rather than just a least square norm. But other than that, you have basically a convolution here again. We've seen convolutions before. So convolution of the blur kernel of the LEDs with the values of the LEDs, and then pointwise multiplication with the LCD panel pixels. And that should ideally be similar to the target image in some metric which is not defined at this point. Okay, so that's basically the kind of thing that you want to do. There was some prototypes of this. There was a startup company called Brightside Technologies that was founded and was actually very successful and sold to Dolby back in 2007. Gervin worked for that company for a number of years, both for Brightside and then later for Dolby. And so this is kind of a commercialization timeline. So when this acquisition happened, and Dolby also created a research chair for me here at UBC. And really around 2012 or so, this really became the major dominant TV technology in North America. So that basically you go to Future Shop now and you buy a sort of mid-range to high-end television with then you get probably something like this in the television, right? So we haven't really been giving up on this. So this is recent work with Gervin on basically doing high dynamic range projection. And so the idea with projection is that you have to be very, very careful about how you spend your light. I mean, you cannot just increase the brightness of your light sources more and more. And so the idea here is, rather than absorbing light, let's refocus the light. So if you imagine if we have a lens here, we can actually create a super bright spot on the screen here, and you know that's basically super white, right? Much brighter than if we distribute the light uniformly. And then that results in an optimization problem where you basically want to define some arbitrary phase function here in this plane that actually gives us a low resolution approximation of our target image. And I don't have time to go into the math, but basically you can do this. You can do this both for fabricating 3D freeform lenses that give you certain kinds of caustic images, as it's called, or you can actually do diffraction gratings that were built at KAUST again that give you these low resolution images. Or you can actually combine this in a high dynamic range projector, which is what NTT and Gervin are doing. So where basically this is now a phase-only digital modulator that you can program like a normal screen, and you program it to do these masks, and then basically once you propagate it, you get a low-resolution version of your image, which is then cleaned up with a high-resolution regular unit. So you can, of course, when you do this, you get much, much higher brightness values than before. So this is MTT, which is a local startup. Gervin is one of the founders of this company, and that's going on right now. Okay, so I'm running out of time, so I'm going to skip the audio stereoscopic displays. It was just another display project we did on glasses-free 3D. I do want to spend a few minutes to talk about what ties all of this together. So the computational methodology here is really that we're solving a lot of inverse problems. Okay, so this is really the at the heart of all of this. Okay, so we have basically you know, a forward problem, as you know, you have some physical properties and parameters, and you simulate them to get observations. Inverse problems is you have some observations or target observations, and you basically try to infer model parameters from that. And typically, since we're working with light, we'll have something that looks at first sight relatively simple, because we have usually linear inverse problems. Okay, so we have light interaction with matter is mostly linear. Okay, so we have something like this. There could be variants. So rather than having a matrix vector multiplication here, you might have a matrix factorization problem, or non-negative matrix factorization problem, or something along those lines. And then when you do this thing describes your optical system. And then once you have your unknown thing interact with your physical system, it should be similar to something that you've measured, or that's your target image or whatever. Unfortunately, this thing is usually poorly conditioned, because otherwise where would be the fun, right? And then you need to regularize. And so basically, when you look at this equation and similar equations like this, you have a lot of things that you can work on as a computational imaging researcher. You can work, first of all, well, you get to define what A is. Okay, you design the optical system. You get to decide what optical. First of all, what kind of imaging system you want to build, whether you want to build a hyperspectral imager or light field imager or whatever. So you and then you get to decide how to design it, right? So this is the A matrix, and of course we want to create A matrices that are as well conditioned as possible to make the rest of the thing easier. So this is the optics part, where we're basically designing as A matrix. Typically, we're not going to succeed in something that's a super easy A, so you need these regularizers. And the regularizers are basically priors, okay? So they are priors about what it is that you want to reconstruct, whether that's 2D images, 2D hyperspectral images, 4D light fields, 3D volumes, what you name it, right? Every one of those will have different statistics for, and you know, maybe you might have application specific, but maybe you want to work in microscopy. Well, I mean, your prior is probably going to be something cell related, right? So there were very application specific priors that you can develop. And then finally, you know, here I just have the L2 norm, which is, you know, sometimes reasonable, sometimes not, right? Sometimes you know, I mean, this assumes Gaussian noise, I don't need to tell you, but, you know, sometimes you have Poisson noise. Sometimes, like in the display space, you don't really care about something like a Gaussian noise or whatever. You just want the images to look as closely to the target as possible, and then you have sort of some kind of perceptual metric here, which can be computationally extremely difficult to bring down to a point where you can actually use it in practice. So all of these components you can actually work on. You can write papers on what are good image priors. You can write papers on what are good A matrices and how do we build them. You can write joint papers where, you know, you have these different components and they plug together in just the right way. All of this is possible. The priors typically tend to be based on sparsity. Okay, so we have, you know, I think most of you know this stuff, right? L1 norms, right? That model some kind of sparsity or maybe low rankness or something along those lines. There's always this trade-off between using sort of weak priors, just like total variation, and that are not very strong priors, but they're very generic, right? So you can apply them in a lot of different settings. And on the other side, end of the spectrum, you have very specific priors where, okay, you go to Paris, you take a photo of the Eiffel Tower, there's 1 million tourists in front of you, and you want to get rid of all the other tourists and replace it with parts of the Eiffel Tower, where you can go online and search for images of the Eiffel Tower and try to complete it, right? But of course, that's a very specific kind of image prior. And somewhere in between, you have things like dedicated bases like wavelets, Fourier transform, and learned bases. Of course, now deep learning fits into this, of course. But also dictionary learning and other kinds of methods, convolutional sparse coding we've worked on a lot. So there's this continuum, and you know, of course, the further you're on this side, the more you have to, I think, work to really convince yourself that what you've learned is actually representative of what you might want to reconstruct. Right? But sparsity is really the underlying principle of all of this. And then the final sort of technical slide here. This kind of framework, okay, with this framework, with these kind of sparsity priors, we actually wrote a paper late 2014 where we basically just say, okay, let's take a standard camera pipeline, which is historically just a bunch of heuristic building blocks, right? So you do denoising, you do color interpolation, all these kinds of steps, 10, 15 steps in many cases. And let's just replace it with a single optimization problem, where all of this is collapsed together in a single problem. And we showed that you can still do this in a modular fashion, by the way. Let's put this together. It becomes a very, very flexible system that can deal with many, many different image formation problems. But if we just apply it to the most basic image formation problem, which is reconstructing a color image from these what's called a Bayer pattern, which is basically just color interpolation between pixels of different colors, then we can actually get a significant improvement over the state of the art. With this extremely generic method, we can outperform all of the, I don't know, 3,000 or 4,000 dedicated algorithms that have been published for this problem by 2 decibels. Okay, so just a very generic, very well researched area. We came up with this very generic optimization problem and outperforms all the existing methods. So that's called FlexSense. All right, and I'm really running out of time. So now, just a reminder, this is what I'm doing. This is, I think, really this hardware-software co-design business is a very, very powerful, framework for attacking a lot of problems in imaging, and I think it's very promising, not just for sort of this entertainment space, but also for scientific applications and engineering applications. And with that, I just want to thank my collaborators, and I'm available for questions. Thank you. Sorry for going over time a bit. Are there any questions? Yeah.
What is the biggest limitation in making the projectors better in terms of resolution?
Resolution and brightness. Well, I think Gerwin is working on brightness. So I think that what you need to realize is just how tricky it is to make light sources brighter in projectors, right? I mean, basically, you cannot just say, okay, I'm going to take this projector and put a light bulb in that's twice as bright, because all the thermal management will be screwed up and everything will just fall apart. You need to completely re-engineer this device. And then on top of that, you have this problem that the human visual system is ultimately logarithmic, so even a factor 2 increase in the brightness will be barely noticeable, right? I mean, it will be just one delta t, one delta in you get basically one more pixel value. This is really a problem. So I think this notion of using light, redirecting light, steering light around is actually a very powerful one, because on average, of course, the slides are a bad example because it's white background, right? But if you have a natural image, right, then the average intensity of this not natural image is maybe 18% of peak luminance of the projector, right? So what you do in a traditional projector design is that the light source creates light and illuminates the whole frame, and then the light modulator that's in the projector absorbs the light where it's not needed. So if you really have this 18% intensity on average, that means that 82% of the light is just absorbed. And so it makes much more sense to recycle that light and use it for making the bright spots that do exist in the image brighter. And then you can make you can find different trade-offs. You can either make the light source dimmer, or you can save power, or you can have much punchier images for the same power budget, things like that. Now, for contrast, of course, one thing that you do have to be careful about is that in a room like this, of course, you will never get great contrast in the projection system because, okay, so here's a standard thing that I like to do in my class. Let me just find the right slide. All right, okay, so what color is this? Black? What color is this? Right, so basically, right, this is slightly brighter than this, right? But so that, if we switch the projector off, you would all say that this is white, right? So basically, this is the contrast in a room like this is limited by ambient illumination, right? So really high dynamic range projection is really makes most sense when you talk about controlled lighting environments like movie theaters or good quality home theaters, where you control all the ambient lighting. Yeah.
Thank you very much for the presentation. It was fantastic. So many interesting things. Actually, I have a question on the fluid imaging project that you were mentioning. So I realized that you are using like a very, somehow I would say, controlled environment, right? A specific background pattern that you
Right.
vertical flow.
Yeah.
Like that. So have you tried it in a less controlled environment?
You can do that. I mean, so there are some works on Transient Imaging where you just use natural backgrounds. I mean, basically what we're solving for the early stage of that is an optical flow problem. Optical flow only works if you have high frequency information to track, right? Basically, if I have a solid white background, you will not see the distortion, right? But you know, leaves of trees, tree foliage, grass, or whatever, is actually in practice good enough to get a good amount of information. Maybe not as good as these custom patterns that we designed, but you know, some people are doing that. Now, of course, if you go outdoors, you still, if you want to get the 3D, you still have to have a calibrated camera array and all those kinds of things. So then it gets a little bit more complicated, and by the time you have a calibrated camera array, you might as well put some background up as well, right? So, but if you're just looking at the 2D imaging, you can certainly do that with just a single camera, and if you get lucky with the background.
So actually, I was thinking about whether or not this approach can be used for dynamic and random texture modeling, because I just saw that you modeled the flow of the heat very nicely.
Yeah.
So I was really curious to see whether you can also model like the flow of smoke or random texture.
Yeah, so we had other papers, and I just had a hint with one slide of animation. We had a whole bunch of papers for imaging fluids, for computer graphics kind of applications mostly. We didn't spend enough time for the scientific community. We didn't spend enough time to verify the measurements because we don't have we don't have the resources to do comparison setups, with all the instrumentation needed to get ground truth data. So we did it all only through simulation. But I'm actually quite happy that a lot of this work is actually very heavily cited from the fluid imaging community as well. So there is something there, but we couldn't publish in fluid imaging without spending tens of thousands of dollars just to build validation setups, basically. So that wasn't possible. Good.
Yeah. Okay, could you say a little bit about sort of L2 norm versus perception norm? Like, is it like I would imagine, yeah, you don't want to have to optimize over some very hard to model perception norm. On the other hand, is it true, for example, that if the L2 is kind of small enough that you get good enough perceptual?
Yeah, it's more the other way around. I think we can. So here's basically. It's not. So it's not true, unfortunately. I mean, basically the L2 norm is for comparing visual quality. The L2 norm is and SNR and all these other derivatives of L2 norm are only useful if you're comparing similar types of errors. Okay, so if I give you two images with random noise, you can use the L2 norm to decide which one is better. If I give you two images with a bias added, you can use the two L2 norm to compare them. Or if you sign gradings added, whatever. As long as the type is the same, you can use the L2 norm. But imagine, so for example, if you're very sensitive, if I take an image and I add 2 to every pixel, okay? The L2 norm will give me a relatively large error. Visually, it will make virtually no difference. If I add a sign grading with an amplitude of 2 to the image, it will make visually a lot of, depending on the spatial frequency, it will make visually a huge difference, but the L2 error will actually be lower. That's, you really have to be careful. I mean, you can really only use L2 and SNR and all these kinds of things if the error has similar structure.
Okay, good. Awesome. Makes a ton of sense. Great answer. Now I want to understand then your last result, where you have the generic pipeline. Because presumably the optimization that you used was L2. And yet, you're basically claiming to do a lot better than the more complex pipelines for which Where photographs, I would imagine, there's all kinds of possible error modes.
So for the you are referring really for the very last the last slide that I showed there, this one, right?
Yes.
Yeah. Okay. So this is a good point. I mean, your the L2 here. So basically, I think the perceptual metrics are mostly useful when you're talking about displays, because you're directly concerned about the look. Okay. Here, when you look at imaging problems as opposed to display problems,
Okay.
then the norm that you use there is more related to the noise model that you have. So in this case, basically we were implicitly assuming Gaussian noise.
Okay.
But there's a variant of this for Poisson noise, for example, which happens to take over in really low light situations. Then you're all of a sudden with Poisson noise. This pipeline will work if you adapt it to Poisson noise, but if you're just using Gaussian noise, that it's actually Poisson noise, then you're in trouble.
Interesting. Okay, thanks.
But everybody else is also in trouble. That's right? I mean, basically, so
Yeah.
I mean, but there are methods to. Unfortunately, then you need to have models of the noise. You really need to fine-tune your reconstruction to the specific noise model that you have. So we have some work on Poisson noise in particular. And of course, there's now a body of literature on noise estimation. So you could run a first stage which estimates what kind of noise you have, and then you can tune your parameters to that. Not that we've tried that, but I think that should be possible. So another hand earlier, somebody else? Yeah.
In the that time of light imaging, like the looking around the corner and like the depth measurement, I was wondering if you have a problem with the phase ambiguities, like if you're dealing with a modulated signal.
So, well, no, because I think this is exactly what this correlation sensor gives us, is the phase. Now, it's phase of the modulated signal, okay, not phase of the electromagnetic wave, right? So it's right. So and that means that we have a resolution limitation that corresponds to whatever our highest modulation frequency is. So I mentioned that we can, with these cameras, we have modulation frequencies of maybe up to 100 megahertz. If you think about 100 megahertz is 3 meter wavelength at the speed of light. This correlation image sensor discretizes the measurements to something like 10 usable bits. So 3 meters divided by 1,000, we're at about 3 millimeter resolution in almost ideal circumstances. So if you have low albedo or whatever, then it drops below that. But yeah, so that's roughly what you could expect as sort of a rule of thumb.
Any other questions? One thing I forgot to mention in the intro for Wolfgang also is that he is Papers Chair for SIGGRAPH Asia this year in 2016, and also ICCP, International Conference of Computational Photography, which happened.
So ICCP happened last weekend, and the SIGGRAPH Asia Papers deadline was yesterday or the day before? Tuesday. It's all a blur. So I hope you all submitted your papers too. But it's too late to do anything about it now.
All right. So thank you so much for taking time for this in an extremely busy summer, and thank you so much.